Alright, let's continue. Okay, let me open the table of content first. Okay. We are still in chapter 28. This one, log. And still in homework simulation. Let's take a look at that. Okay, we are in this homework simulation section. If I remember correctly, the last time is that we take a look at this question, basically about ticket log, right? Now let's take a look at yield. Okay, now examine yield, in which a yield instruction enable one thread to yield control of the CPU. Realistically, this would be an operating system primitive, but for the simplicity, we assume an instruction does the task. Find a scenario where, okay, we assume an instruction does the task. Find a scenario where test and set with cycle spinning but yield. Okay, does not. Okay. How many instructions are saved? In what scenario do the saving arise? Well, let's check this first, I guess. Yield. Okay. Atomic swap. Okay. If we get 0 back, log is free. Okay. We're done to this one, critical section. Okay, release log. Check if we are still looping. Okay. Oh, this is, I assume, jump, I guess. Jump to this one. But what is yield instruction here? Okay, I yield. I turn negative 2. Like what? What is this yield about? Just count down the interrupt counter to 0 when it gets to 0 or when the yield instruction is issued. Oh, a switch takes place. Key thing, if manual scheduling is done using the uppercase P flag, I guess this uppercase V flag, interrupt must take place every instruction for this to work. Oh, okay. So when we have yield, we immediately switch to another thread. that's why this is return 2. Alright. Okay. And then test and set. Then this one. Oh, not again. Okay. Well, let's try that first, I guess. Trade log. If I remember correctly. Source program, okay. Thread log, yield, and then should we trace AX and mutex maybe? Mutex AX, okay. Count. Well, why not, I guess. What is it called? AX and then PX maybe. So basically if we get the mutex or we get the log, we immediately go into critical section. I assume something like that. So let's check that. Okay. Okay. Yeah, we are in the critical section here. Okay. Release the log, I guess. Okay. Find a scenario where test and set with cycle spinning, but yield does not. Yield does not. Maybe we can do that with interrupt frequency. Change to 3, I guess. So we are interrupting every 3 instruction. Something like that. Okay, interrupt in this one. Okay, maybe not the instruction. Maybe if we are doing that every 3 instruction, we are gonna enter the critical section on thread 0. So we are not really using the yield on any of these thread, I guess. maybe this one. We are using yield on thread 1 and then continue on thread 0, right? Thread 0 release the lock. And on thread 1, we got the lock, I guess. I mean, thread 0 already done. And maybe let's add another iteration. Px equal 1, maybe something like that. So we are not immediately halt, right? Oh, greater than 0. Okay. So maybe not 1 but 2. Because if we provide 1, right, we will immediately not fulfilling this condition. It needs to be greater than 0, which means it needs to at least be 1, if I understand correctly. So let's try this. Okay, this one yield, right? Continuing on thread 0, release the lock. Okay, this one, trying to get the mutex or the lock, I guess. We check, okay. So we are moving back to the top here. Right. And then we got the mutex on thread 1 here. Okay, we check, alright. Acquire done. Oh, we release the mutex. And then yield. Okay, I think this is kind of interesting. Is it one of those, what is it called? Wake up, waiting race. With just the wrong timing, a thread will about to park, assuming that it should sleep until the lock is no longer held. A switch at that time to another thread, say a thread holding the lock, could lead to trouble. For example, if the thread then releases the lock, the subsequent park by the first thread would then sleep forever, potentially. Okay, so before we are going to release the mutex or the lock, not before. Yeah, maybe before we are going to release the lock, thread 0 already check the mutex, and well, it yield the, what is it called, the CPU. So it sleep, and then what is it called, that one keep going. In this case, fortunately, the interrupt is short, I guess. So thread 0 did not sleep for too long, maybe something like that. jump. Okay, going back again, check the mutex. Okay. Alright, so because that 0 is the one to get the mutex first, or the lock first, thread 1 is gonna yield, I guess, right? And then this one. Okay. Greater than this. I'm not sure if what is it called? If that scenario make test and set recycle spinning. Let me check again. You know what? Let me copy this. Put that in here. But we change this to test and set. Something like this. Let's check. Okay, test. Moving into the critical section, thread 0, this one keep spinning, I guess. Going back to this instruction. Okay, we release the mutex or the lock, and then this one. Oh, okay. Yeah, we're still spinning in this one. Okay, again. I guess that one get the mutex, right? And thread 0 also try to get the mutex, but the mutex is already in thread 1. So that one going into the critical section, and thread 0 keep spinning, I guess, until this one release the mutex or release the lock. Okay. Yeah. That 0 spinning again. And then I assume because we already released the lock here. What is it called? That 0 get the lock, and then entering the critical section. And then that one keeps spinning again. Yeah, we released the lock on thread 0 right before thread 1 check for the lock. So I assume, yeah, that one keep going into the critical section. Okay. In this scenario, the wave cycle spinning is not really that much, I guess. But this is maybe, what is it called? The minimum scenario, maybe something like that, to see if there is redundant spinning rather than just passing control to another thread. Maybe something like that. How many instructions are safe? Well, how many instructions are safe in this scenario? Right. Where is it? Okay. Probably around this one, I guess. 3 instructions are safe, at least, because of the spinning. Maybe. In what scenario do this saving arise? In what scenario do this saving arise? In what scenario do this saving arise? Probably when the current thread still holding the lock and interrupt switch to another thread. Again, something like this. We haven't released the lock yet, right? On thread 0, we just enter the, what is it called? We just enter the critical section, and because we haven't released the lock, another thread gonna keep spinning if we use test and set. I assume something like that. Maybe when the current thread have not released the lock, but interrupt switch to another thread. Switch the focus to another thread. In what scenario do this saving arise, right? Maybe that's when the saving arise. Probably when the current thread have not released the lock, but interrupt switch the focus to another thread So the saving of instruction may be something like that. And how many instructions are saved, which I assume means how many instructions we don't need to execute, something like that. Oh, in what scenario to the saving of instruction, the instruction not executed arise probably when the current thread have not released the lock but interrupt switch the focus to another thread. So the saving of instruction arise because rather than we keep spinning the process, we keep spinning on the thread without the lock, we immediately change the focus to another thread. Until we are on the thread with the lock. Maybe something like this. I'm not sure if this is correct or not. But from my understanding, the saving arise, maybe that's the word. The saving arise when the current thread have not released the lock and suddenly there's interrupt, right? So rather than waiting on another thread that doesn't have the lock, we immediately switch to another thread, and hopefully we are switching on the thread with the lock. If not, then we keep switching the thread, I assume. Something like that. Okay. In what scenario? Okay. Finally examine test and set. Okay. We are doing multiple tests, I assume. Okay. When I see this name, it reminds me of the joke like final, hopefully final kind of file, when we got revision over and over again. What does this log do? What kind of saving does it introduce as compared to test and set? Okay. Test and set. Okay, let's take a look at this. On the, what is it called? On the left, I guess it is test and set. On the right, it is test and set. Let's take a look side by side. Okay, atomic swap. Oh, interesting. Remove mutex. Okay. We copy the value in mutex to the, what is it called? to the AX, register AX, and then check if it is equal 0 or not. If it is equal 0, if not equal 0, I mean, if not equal 0, we are going back to this. Oh, interesting. If it is not equal 0, we are going back to this. So the spinning, I assume, is more straightforward maybe. And then after that we also test again in this. Oh, in this scenario, in this instruction, I mean, it is the same as this one. So yeah, there are two kind of tests thing, I assume. So first we test the mutex itself without trying to change the mutex value. And then if we, what is it called? If we are sure that the mutex equals 0, then we try to, what is it called? To change the mutex value, but also test, right? Are we, what is it called? Are we success in changing the mutex value or not? Because again, the interrupt can happen right before we are trying to get the mutex or the log. So we still need to check that, right? So there are two tests here. I mean, like the name suggests, I guess. Test and set. So this is the first test, and this is the test and set. I assume something like that. But then again, the spinning might be faster on this case, but I'm not sure if this is safer than the test and set. Okay. What does this log do? Well, basically we check first, what is it called? We check the value of the mutex as is without trying to set or without trying to get the log. Maybe something like that. Okay. Try to check the mutex value without set the mutex, something like that. And then this one we test and set, right? I'm not sure if that is gonna save some instruction not being run. I mean, well, maybe it's safe when we have those interrupt, I guess. Maybe. Yeah, I'm not sure. Let me try that. test and set. Alright. Okay. Test here. Okay. Oh, okay. So because the interrupt happened right before we jump, right? But of this thread didn't really get the lock yet, and then the thread 0, right? The thread 0 get the lock, so the thread 1 need to wait. Yeah, maybe this is one of the downside with this test and set, because if the interrupt happen right before the test and set, we are running 3 more instructions, I guess. Okay, and then this one. I mean, this is the usual test, right? Okay, acquire, entering the critical section on thread 1. Here, we jump back to check the mutex, right? And then after that we release the mutex. Okay, and then okay, because previously the mutex is not 0, we are going back, right, to this instruction. Okay, and this one, oh, back to check again, check the mutex again. And then on thread 1, we got the mutex here. And then on thread 0, oh, interesting. Okay, because we previously checked only the mutex without taking up the mutex, we are going into the test and set on thread 0, maybe something like that. And then move, okay, and then we are entering the critical section on thread 1. Okay, release the mutex, right? And then after we release the mutex, that 0 going back up and test the mutex again. Only test, no set in this instruction. Okay, and then going back, and then that 0 get the mutex here. Okay, check the mutex. Enter in critical section. Check the mutex again. release the mutex. Okay. Check the mutex again. We keep spinning on thread 1, I guess. And then hold on the on the thread 0. Okay. And then keep going on thread 1. So I'm not sure if there are any savings, especially if the interrupt is quite short. Maybe there are some kind of saving of the interaction if we, what is it called? If we have more interrupt frequency, or not more, if we have long interrupt frequency, maybe something like that, instead of interrupt every 3 instruction. Maybe if we have interrupt every 6 instruction, but again, I assume maybe that's not gonna change much. Or maybe not 6 but 7. I mean, we have these 3 instructions and then these 3 instructions. Okay. Yeah, let's try that. But I don't think it's gonna save that much. See, at least in this case, we keep spinning, right, on thread 1. And then, after we release this, we are finally entering, or we are finally get the log, I guess. We are finally get the log on thread 1. So this one is gonna keep spinning. The thread 0, I mean, until it is got release. Okay. Keep spinning, alright. And well, because we use the old value of mutex here, the test gonna be false, I guess. So we keep spinning again. And fortunately, because there is one extra instruction before interrupt, we are starting to get into the test and set part. This one also the same, right? Into test and set part. But the thread 0, what is it called? The thread 0 get the mutex instead of thread 1. Something to keep in mind. And then hard. Okay. Yeah, I'm not sure if that is gonna save some instruction though. I mean, maybe because we are, what is it called, pushing back this test and set instruction, but this one is still keep spinning, I guess. Let me check. Okay, release the mutex. Alright, acquire. Okay. So we are trying to get the mutex here, but thread 1 got the mutex first. So this one gonna keep spinning until the mutex release on thread 1. Okay, this one, the thread 0 get the mutex finally. Okay. Yeah, I'm not really sure if we save any instruction by using test and test here. Test and set. Let me check. 1, 2, 3, 4, 5, 6. Maybe we can calculate the saving of instruction like that. I'm not really sure. 1, 2, 3, 4, 5, 6. Yeah, I'm not really sure if test and set have any kind of saving or instruction that we don't need to run compared to the test and set. Yeah, I'm not sure about this one currently. Okay. Hello, ping pong poing. Welcome. Yeah, we are still in chapter 28, learning about log for the concurrency here. Yeah, it's getting confusing, I guess, but I will take my time understanding this, and we are at the final question here, which I'm not sure if there is any kind of instruction save or the instruction that we don't need to run with this code test and set compared to test and set. So there is that. And maybe after this I will go to this chapter. Still a long way to go. Yeah, it is still a long way to go. There are more chapter. Good luck, and you can do it. Thank you. Okay, condition variable, and there's also semaphore. Okay, common concurrency problem. Okay, event-based concurrency, advanced. Let me take a break. Oh, hello, Headstrong. Did you end up understanding what Yield is doing in test and set? Okay, so if I understand correctly, what the Yield doing here is that rather than we are, what is it called? Rather than we keep spinning to check the mutex, we immediately switch to another thread, and maybe at later on, what is it called? We will going into the thread that have the lock, so that thread can keep going, I guess. So if I understand correctly, this will save some CPU cycle because we are not spinning and just give up control of the CPU and let another thread keep going. If I understand correctly, something like that. But yeah, correct me if I'm wrong. If not, yield and try again. Compared to test and set, right? In test and set, we keep checking the mutex. I actually don't understand. Oh, yep, that's correct. Most modern multi-threading code use the yield primitive under the hood. Okay. On Linux, almost all multi-thread primitive use the Fulltext API to do the yielding. Oh. Okay, yeah, I'm still not sure about the Fulltext here. I haven't tried that yet. Okay. Ping Pong Point said, actually don't understand, but I like seeing someone with big dedication like you. Okay. I've been busy, so I really watch your stream. Sorry. No worries. Yeah, just going to my stream whenever you can. Don't force it, I guess. Okay, Headstone said it took Windows a while to get the same API, which it calls wait on address. So there's still a fair bit of code that use other yielding primitive, but new code seems to be increasingly moving over. Oh, there's a fair bit of code that use other yielding primitive, but new code seems to be increasingly moving over. Okay, interesting. Yeah, I haven't taken a look at the Windows API yet. I mean, I haven't taken a look at the Linux API too, I guess. So I need to focus on that first. Okay, so the difference, right, between yielding and also test and set. Right, and I'm also, what is it called? I'm kind of interesting in this, what is it called, mechanism too, in this test and set, right? I'm not sure if I missed something, but it looks like the book have this question, one kind of saving does it introduce us compared to test and set. Let me show that, I guess. Set by set, this is test and set, and this is test and set. So basically we have one more test without set, and then going into the test and set mechanism. So I'm not sure if doing this gonna save any instruction. I mean, is it gonna make us not, what is it called, not waste CPU cycle execute the instruction? Maybe that's the word. Okay, let me, is test and set gonna save some CPU cycles to not run the instruction compared to test and set. Yeah, this is what I'm kind of curious, at least according to this book wording, right? So maybe I'm missing something here. So I didn't read the entire chapter in depth, but when I skimmed through it, I didn't see information you would need to fully answer question 14. Maybe it was covered in previous chapter. Okay. In the previous chapter, yeah, I'm not sure. I mean, we take a look at test and set. Where is it? This one, I guess. Working spin lock with test and set. Maybe in this one. But yeah, we haven't taken a look at lock yet. So yeah, maybe I will take a look or revisit previous chapter too. But this is kind of interesting. It has to do with the way CPU implement atomic operation. Anytime you perform an atomic operation like CMP XGSG, it needs to communicate with other cores to make that instruction. Oh, so it has to do with the way the CPU implement atomic operation. Okay. Running a bunch of atomic operation in a type loop generates a lot of traffic on the core-to-core communication mechanism. Oh, okay. Yeah, I didn't know about that. Okay. So it's gonna generate a lot of traffic on the core-to-core communication mechanism. I see. So maybe the saving in here means, so if you use normal non-atomic operation first, like test and set, you skip most of that traffic. Okay. Yeah. That's what is it called? That's what I'm not sure yet, I guess. Maybe I missed something, right? And it turns out I missed something. Okay, so it has anything to do with the atomic operation. Okay. It generates a lot of traffic. So maybe okay, let me try explaining this. What is it called? If we try to use atomic operation, in a tight loop, no. Atomic operation need to communicate. Okay, need to communicate with its other CPU cores to make the operation works, I guess. To make the operation works, running a bunch. Okay, so running a bunch of atomic operation in a tight loop will generate a lot of traffic. On the core mechanism. Okay, traffic on the core-to-core mechanism. With that in mind, something like that, using the normal check or the non-atomic operation before the atomic operation will prevent us to go into how do I explain this? In mind, using the non-atomic will prevent generating traffic, or maybe reduce, I guess, reduce the traffic on the core-to-core mechanism. Question mark. additional detail to this is that if the memory address being compared exchange is not contended, no other thread are trying to take the log, no core-to-core communication is generated. Oh, okay. So if there are no other threads trying to take the log, no core-to-core communication is generated. Okay. Let me check. To make the operation work, so running. On the other hand, okay, we generate a lot of traffic on the call. Assuming we generate a lot of traffic on the core-to-core mechanism, assuming there are other threads trying to get. Okay, as a side note, if there are no other threads trying to take the log, the atomic operation will not generate. Okay, will not need core-to-core mechanism, I guess, or will not generate core-to-core communication traffic. Maybe something like this. If there are no other threads trying to take the log, the atomic operation will not generate core-to-core communication traffic. And the core-to-core communication. Okay, so the optimization only makes a difference if the log is highly contended. Okay, so the optimization. Oh, all right. So there is this, what is it called? Some kind of optimization in this test and set if the log is contended with a lot of thread. Maybe something like that. So the optimization on test and set is will have any effect, or how is the wording here? So the optimization on test and set maybe something like that. Gonna save some GPU cycle, maybe something like that. Gonna save some CPU cycle if the log is highly contended across a lot of threads, maybe something like that. Okay, maybe. Alright, yeah, this is new information to me. I mean, I'm still not sure about atomic operation yet. I haven't gone there. You save traffic on the core-to-core communication, which will improve performance of all atomic operation running at the same time. Okay. Oh, wait a minute. Gonna save some. You will save traffic on the core-to-core communication, which will improve performance. Or maybe something like this. Will improve performance the optimization on test and set will improve performance if the log is highly contended across a lot of threads. Maybe something like that. You save traffic on the core-to-core communication, which will improve performance of all atomic operation running at the same time. Okay. Yeah, this atomic operation is kind of new to me. I only know about atomic as either all or nothing. Yeah, only that. But I'm not sure what happened under the hood. Okay. Alright, this one. Using non-atomic operation. Okay. Alright, I will put this on the repo later on. And maybe on the next session we will going to this chapter, I guess, log-based concurrent data structure. Okay, yeah. I'm not sure what we will see in here. Maybe more confusion for me. But we will see. Okay. Alright, so I guess that's it for now. I will continue on this chapter on the next session. And it looks like we are gonna have to write some code here. It is kind of exciting, I guess. Yeah, personally I prefer the homework code rather than the simulation. But sometimes we need the simulation to understand the concept, right? So there is that. But we will write some code probably. And oh, for the currency here, it looks like we have homework code. A lot of it. Okay, interesting. Alright, but first I need to read this chapter first. Okay. Okay, that's it for now. Thank you for watching and see you next time. Bye bye.